Hey guys, Tony DeMore here from DeMore Engineering. Welcome to video 2 in the DeMore Engineering University series. Today we're going to do DC power, but first we're going to answer last week's homework question, which was we have a 12 volt system and we want to light up an LED, and we needed to figure out what resistor, what value we needed so that we could have 10 milliamps of current, which we did last week. We figured out we needed a 1 kilo ohm resistor. That's cool. The homework problem was, how much power does the resistor need to be able to handle? Because that's another spec that you need to spec when you're choosing a resistor. So we can use the Ohm's law, the power laws for that, which would be you can have the voltage squared divided by the resistance. That'll give us power. We could do volts times amps. That'll give us power. We could also do amps squared times the resistance. That would give us power. Any of those three would work for this. Well, we need to know the voltage across here first. Well, we know there's 12 here, there's 0 here because that's ground, and there's 2 volts up here because of the 2 volt loss across the LED. So there's 12 here and 2 there. That means that there's 10 across here. 12 there, 2 here, so there's 10 volts from here to here on this resistor. So that's what we use for our formula. So for the first one, we would have 10 squared over 1K, it's going to equal 100 over 1K, and that's going to equal 0.1 watts, or 100 milliwatts. If we use this formula, we would say 10 volts times 10 milliamps. And if we use this one, we would say 10 milliamps squared times 1,000 ohms, or 1K, and we would also get 100 milliwatts, any of those three. So if you said 100 milliwatts, good job. And now let's get into some more difficult DC power stuff. So let's talk about DC power a little bit. Here we got a circuit, 12 volt battery, 3 resistors. They're 4 ohms each. They're in series. This would be called series, just like when you're talking about your voice coils on your speakers, you're saying, you know, should I put them in parallel or series? This is a series connection. When you put resistance in series, they add together, so 4, 8, 12. So this whole thing is 12 ohms. So how much current? Let's figure out, we want to figure out how much power is going to each one of these loads. But first we need to know how much current is going through there. And we know that, one of our equations, we know that amps is volts divided by ohms. Well, we have 12 volts. 12 volts is here, and this is ground, so this is 0. So we have 12 divided by, these add up, 12 ohms, or 1 amp. Okay? So we know we have 1 amp of current flowing through here. So now we can use one of our power formulas. I like to use the, in this case, probably the amp squared times resistance formula. That one works out pretty easy, especially in this problem. So for each resistor here, amps is 1 amp, so 1 squared is 1 times 4 times the 4 ohm load here, so 1 amp squared times 4 ohm load, so 4 watts. And we're going to see that on all these. 4 watts, 4 watts. So that means that you add all these up and it's dissipating a total of 12 watts, which makes sense because the whole circuit has 12 volts with 1 amp going through it, so the battery is putting out 12 watts of power. And they're split up like that. That's a DC series power circuit. Alright, let's talk about DC power and when things are in parallel now. So let's take our same loads, those same 4 ohm loads, and let's put them in parallel. Parallel means that the loads are connected at exactly the same place in the circuit on both ends. So you can see all these resistors here are hooked to 12 volts on the top, and they're all hooked to ground on the bottom. So this is 12 volts, all of this, and this is ground, all of this. So these are our same 4 ohm loads that we used in our other example. 4 ohms, and 4 ohms. And on this one, I think it would be easy to figure out, we got to figure out the currents here. So I think it'd be the best way to figure out this current to just say that amps equals volts over ohms, probably a pretty handy one here. So we can see we have 12 volts, 4 ohms, 12 divided by 4 equals 3 amps. So this resistor here has 3 amps going through it this way. And this one is also hooked to 12 volts. There's 12 volts up here as well. It's all one big connected common circuit. 3 amps here and also 3 amps here. So the total current leaving the battery here will be 9 amps. It's like a freeway. It's like a wide freeway here. 9 amps going down it. And then they all take their own little route, and there's 3 amps on each one of those little branches. So that's how that works out. How about power? How much power is in these loads here? Well, we can do, let's do the, I think for this one we'll do power equals volts times amps. Voltage across this resistor, there's 12 here and 0 here, so 12 volts. The current is 3 amps, 36 watts. So each of these has 36 watts of power being dissipated in the resistor for a total of 108 watts coming out of the battery. So that's how a parallel circuit works. Oh, I guess before I continue on, let's just figure out one more thing. What are 3 4-ohm loads in parallel? What's the final load? Well, the final load is going to be what's on our battery here, or if these were speakers, this could be our amplifier here. So what kind of load does this put on our amp? Well, we can see we have 12 volts and 9 amps, and one of the Ohm's law things we can say that resistance is volts over amps. When we figure that out, we're going to get 1.3333333 ohms. So there you go, 3 4-ohm loads in parallel, 1.33 ohms. Alright, we'll do another one here. This one's got a mix of series and parallel elements in it. One thing we need to know is how to calculate, like in the one that we did, the last two, the series and parallel circuits, we were able to prove that when you series up loads, the resistance just adds, and when you put them in parallel, we proved it a different way. We didn't really have a way of showing what actually happened. So if you have loads in series, like I said, they just add together, so we can say load, well, that's the symbol for inductor. Let's not do that. We'll say resistor 1 plus resistor 2 plus resistor 3 equals the final resistance. This is for a series circuit. When you have parallel loads, it looks like this. We have some fractions to deal with. So in the last example we did where we had 3 4-ohm loads in parallel, or 3 4-ohm speakers in parallel, we ended up with 1.33 ohms. And so the way this formula works is you would say, okay, 1 over 4 plus 1 over 4 plus 1 over 4. And in fractions, you get a common denominator, which they already are, and then you add these together. So this whole thing equals 3/4. And since the answer is 1 over the final resistance, that's what this is here, you have to flip it to just get the final resistance. So if you flip this, you invert it. So this is your final answer for 3 4-ohm loads in parallel, 1.3333. Okay, if we know that, once we know the two rules there for series and parallel resistances or loads, we can solve this problem. This problem has a combination here. We have a 4-ohm load that's in parallel with a 4-ohm load. We know they're in parallel because they're connected at the same point on both sides. They're connected at the same point here, and they're both connected to ground here. So these are in parallel. These are in series. So if these are in parallel, we can say, well, let's just redraw this so it doesn't look so confusing. So that's the same exact circuit, we just redrew it. And then we know that the two 4 ohm loads in parallel is 2 ohms, but we can prove it with that math that we just learned. 1 over 4 plus 1 over 4 equals 2 over 4. We invert this, it's 4 over 2 or 2 ohms. So since we can prove that, we can just erase this and call this a 2 ohm load for now, just so we can solve it. Alright, so now it looks a little bit easier. Now it looks like just a straight series circuit. 4 ohms, 2 ohms in series. So the total, using our series math here, 4 ohms plus 2 ohms in series is 6 ohms. So this whole thing from here to here has 6 ohms. 12 volts into 6 ohms. Amps equals volts over ohms. 12 volts, 6 ohms equals 2 amps. So leaving the battery, we have 2 amps of current. 2 amps, we're going to find the voltage drop now, or the voltage across this guy. So volts equals amps times ohms. 2 amps times 4 ohms equals 8 volts. So that says that from here to here, this 2 amps as it goes through here, across this load is going to lose 8 volts, or drop 8 volts. So if there's 12 volts here, and this thing's going to drop 8, then we know that there's 4 volts there at that point. Once we know there's 4 volts at that point, we can redraw our circuit the way it was. 4 ohms, 4 ohms. And we can say that 4 volts across 4 ohms is going to be 1 amp, right? Because 4 volts divided by 4 ohms equals 1 amp. And the same thing here, 4 volts, 4 ohms, 1 amp. And you can just do a sanity check and just check it all and make sure it looks right. Well, there's 2 amps leaving the battery. They're leaving somewhere, they got to go somewhere. So they're leaving here, well here they're going. They're going down this freeway here, and then they're taking their own paths. 1 amp is going that way, 1 amp is going that way. So now let's figure out the power of all of these things. This resistor is 4 ohms and it has all 2 amps going through it. Power equals amps squared times ohms. So 2 amps squared times 4 ohms, or 4 times 4, 16 watts. So this one's got 16 watts of heat, or of power. This one's got an amp and this one has an amp. So 1 squared is 1, 1 times 4 is 4, so this has 4 watts. Same thing here, 4 watts. So we got 16 watts, 4 watts, 4 watts, that's a total of 24 watts. 24 watts total power in the circuit, and again you can sanity check it and say, well, over here at the battery we've got 12 volts and 2 amps. Well, volts times amps equals watts. 12 times 2 is 24, so we know we're right, we know we did it right, and there it all is. Do a couple quick applications real quick. I know we're not talking about AC yet, so I hesitate to talk about subwoofers and speaker loads, but we'll just talk about them as resistors right now. Let's just pretend that our subwoofers are resistors. So let's see if we can get a single 2 ohm load out of 4 dual 4 ohm subwoofers. So I'm just going to draw the 4 speakers here, and each one of these has a 4 ohm load. Drawing them as 4 ohm resistors here. Those would be like the terminals on the speakers, etc. Okay, so what would that circuit look like? Well, we're doing DC, so I'm drawing a battery, not an amplifier. So here's our battery. And let's say that it's putting out 12 volts. And we want to see what happens here if we, let's series up the voice coils. So we know if these are 4 ohms each, it's like this. 4 ohms and 4 ohms. When you put them in series, this one looks like this, and then this one looks like this. And that's what happens when you put them in series. You connect the positive of one to the negative of the other. And this is what the finished product looks like. You connect your amplifier here. So it'd be like if this was your subwoofer, you would run a wire from here to this one, and then you'd hook up your amplifier negative here and your amplifier positive there. That would be seriesing this voice coil. So if we do that, schematically it would look like this. 2 4 ohms in series. We know that when you series loads, they just add, so 4 plus 4 is just 8. So you can redraw this driver as just a single 8 ohm load. And let's put all of those, once they're all seriesed, we'll put them all in parallel. So it would be like 4 8 ohm loads in parallel like this. And these are all grounded. No sense drawing the ground symbol 4 times there, it's all the same point. 8 ohms, 8 ohms, 8 ohms, 8 ohms. Now, we could just do this formula and put 8, 8, 8, and another one 8, and add them all up, and we would get 4 over 8, and then you would flip it, and that would say 8 over 4, and that'd be 2. 2 ohms is the answer. But we can also figure it out using some Ohm's Law stuff that we've learned, because we have 12 volts here, and this is 8 ohms, so the current here is 12 volts by 8 ohms, or 1.5 amps. So we have 1.5 amps going this way. This is the same thing, 1.5 amps, and again and again. So if 1.5 amps is going through each one of these roads, how many amps need to be coming on this main road here? Well, enough to do all these, so it would be the sum of all these, so 6 amps would be going this way. 6 amps, and then 1.5 of them go down each path. The total is 6. We can see here, our battery is 12 volts divided by 6 amps, 2 ohms. So there's the math just to prove that that's right. And it's kind of a practical application for it. Alright, another quick practical application. Let's pretend that we've got 2 loads in parallel and they are different resistance loads. Let's say that this one is 8 ohm and this one is 4 ohm. And you can see they're in parallel here. You know, like we've all known somebody who puts an 8 ohm and a 4 ohm speaker together, or maybe we've done it ourselves at some point in life. I'm sure I've done it at some point. So let's figure out what happens exactly when you do this. So this is 12 volts, and we want to figure out the total current coming out of here, or the current going through these, so that then we can figure out the power. That's one way of doing it, and that's the way we're going to work it out, just because it's more explanatory, I think. We could use our awesome formula here for parallel and say, well, what's the total load on this battery, because these are in parallel. If we did that, do it over here on the side, we would say 1 over 8 plus 1 over 4. Well, you can't add fractions like that because of the whole common denominator business, so you would have to get a common denominator here. So it would end up being 1 over 8 plus 2 over 8, which is equal 3 over 8, and then you flip that around and you get 8 over 3, or 2.66666 ohms. Lots of sixes. But let's just do it another way. We know we have 12 volts here. This whole top rail here is 12 volts because these are in parallel. They're connected to the same place on top and bottom. So if there's 12 volts and 0 volts here, there's 12 volts across this resistor. Current is volts over ohms. So we have, for this resistor, we have 12 volts and 8 ohms, or 1.5 amps of current. 1.5 amps going this way. Apply that same formula here. 12 volts over 4 ohms. This is going to equal 3 amps. So this one has 3 amps going through it. Well, if there's 1.5 amps going down this road and 3 amps going down this road, then that means over here at the source there must be 4.5 amps leaving the battery, because the total of all these loads has to equal what's coming out of our source here. So we have 4.5 amps total, we could figure out, now let's figure out what happens to the power on these situations. Well, easy one here would just be volts times amps. Power equals volts times amps. So we've got 12 volts and 1.5 amps. So the power on this resistor is 12 times 1.5, which would equal 18 watts. 18 watts on this guy. This one's going to be 12 volts times 3 amps, or 36 watts on this guy. So that would mean the total power leaving our batteries, the total of this, 18 plus 36, would be 54 watts are coming out of our battery there. If we wanted to prove that, we could just multiply the voltage at the battery times the total current out of the battery and see that 12 times 4.5 equals 54. We could also say, check this math here and say, well, the total load should be 2.67 ohms. So what happens if you divide voltage by ohms? You should get this current, which you also would if you worked out. So there's one practical example. Another one. And that'll bring us to this week's homework problem. So the last one we just did was 2 unequal loads in parallel. Now we're going to do 2 unequal loads in series. There's our trusty 12-volt battery. Ground. 8 ohms and a 4 ohm in series. Homework question is, what is the total current? And how much power is going through the 8 ohm and how much power is going through the 4 ohm? There you go. Look forward to seeing your responses. Leave your answer to the homework problem in the comments below, and I'll answer it on the next installment. Thanks.